All right, 15.2. I hope you've had your caffeine, you're wide awake and ready for this lesson, because it is a fun one. And by fun, I mean it might be a little challenging, but that's okay, it's fun. All right, so in 15.1, we learned the basic power rule, okay? The problem is, just like in derivatives, sometimes we don't always have just x raised to the n. Sometimes we have, as we used to say in derivatives, we have junk to the n, like we do right here, junk to the fourth. And then we had to go through in derivatives and do the chain rule and all that stuff. The good news is we don't have a ton more rules at all to learn. Okay, we have one. That's it. What we want to do is called U-Substitution. And what that means is we want to replace everything in the problem with U's. And we're going to turn this back into an easy problem. Okay? And the best way I can explain it is to just jump in. So here we go. So when choosing your U, I'm going to give you hints along the way. The first big hint is if you have a bunch of stuff raised to a power, then that stuff is your U. Okay? Bunch of stuff raised to a power, then that stuff is your U. So on example 1, part A, we have the integral of all of this to the 4 times 10x dx. So I'm going to replace this stuff right there. That's going to be my U. So I'm going to let U equal 5x squared minus 3. Now, very important, I even wrote it on here and I'm going to highlight it on here. Do not mix your x's and your u's. So I'm going to start rewriting my problem with u's. In place of that term there, I'm going to put u to the 4th. What you don't want to do is say times 10x dx, because then you just mixed your x's and u's, and you never want to do that. What we want to do now is we need to replace 10x dx with something that equals it exactly. The way we find something that equals it exactly is we take our u term over here, and we're going to take the derivative of everything with respect to x, because we're doing this with respect to x there. So if I take the derivative of u, I get 1, but I just took the derivative of u with respect to x. And that equals 10x to the 1 dx dx, which we don't have to write, plus 0. Now this is the only time I'm ever going to go through these formal motions here, because you'll see watch what is about to happen. If this is over 1, I can cross multiply, and I have du times 1 equals, if I cross multiply here, I'd have 10x dx. We always want to end up with du equals something, okay? So instead of doing du dx each time, you'll probably just see me write du on this side and dx on that side, but this is how come it works. And what a coincidence! 10x dx, it happens to equal du. Will that happen every time? Of course not, but we're just learning. So here we go. So in place of 10x dx, since it equals du, I will replace it. And voila, we just took this complicated looking problem right there and turned it into a basic problem from 15.1. So what I'm going to do is integrate this problem with respect to u. So I have u to the 4th, that will become u to the 5th divided by 5 plus c, which is 1/5 u to the 5th plus c, and at the very end, you've got to replace your u. So I'm going to have 1/5, and I'm going to replace my u with what it equaled. It equaled 5x squared minus 3 to the 5th plus c. Yay! If you didn't catch that, it's okay. We're going to do like 1,000 more. Here we go. So on this next one, I have a bunch of stuff to the power there. So I'm going to let u equal x squared minus 8. So as of right now, I can replace this part with u to the 34th. I still need to replace 6x dx. So I'm going to come over to my u, and I'm going to take the derivative of both sides. The derivative of u is 1, and this is where I would have put du dx, but I'm going to go ahead and put the dx on the other side. Derivative of x squared is 2x, derivative of negative 8 is 0, and I'm going to go ahead and put my dx on this side. So I need something that equals 6x dx in order to replace it, but what I have equals 2x dx. That's not good, but I can make it 6x dx if I multiply both sides by 3. So 3 du equals 3 times 2 is 6x dx. Now I have an exact replacement. So in place of 6x dx, I'm going to replace it with 3 du. So right here, I'm going to put in a 3 du. All right, so once you've replaced all of your x terms with all of your u terms, the next thing I usually do is pull out any numbers. So I'm going to pull my 3 out front. Then I'm going to integrate. So this will be 3u to the 35 divided by 35 plus c. And then I'm going to put my u back in. So I have 3 over 35. I'm going to replace my u, which was x squared minus 8, to the 35th power plus c. All right. Let's keep going. So part C, I have a bunch of stuff to a power, so I'm going to let my u equal 6t minus 10. So as of now, I can replace that part with u to the 5th. I still, however, need to replace dt. And you can't just say, oh, well, I'll just replace dt with du. It doesn't work that way. You have to replace dt with something that equals it exactly. So I'm going to come back to my u, and I'm going to take the derivative of both sides. Derivative of u is 1 du equals, derivative over here, I get 6 dt. So what I have equals 6 dt. I need it just to equal dt by itself. So what do I need to do? Divide both sides by 6. So instead of saying divide both sides by 6, I like to say multiply both sides by 1/6. And now I have an exact match. This right here equals dt. So I will replace it with 1/6 du. Once I have replaced all of my t values with u values, I pull my number out front, and then I'm going to integrate. So this will become u to the 6 divided by 6 plus c. So pretend this is like 6 over 1. Dividing by 6 over 1 is the same thing. I'm going to come off the side. The same thing as multiplying 1/6 times 1/6, u to the 6 plus c. And so I have 1/36, and then I put my u back in. 6t minus 10 to the 6 plus c. All right. This one has a typo. Okay, so I hope y'all are listening to me here. It should say x to the 4th minus 2. X to the 4th minus 2. That is a typo. All right. But we still have a bunch of stuff to a power, so I'm going to let my u equal x to the 5th minus 10x. So since there's a numerator and a denominator, sometimes I split this so that I can see it a little better. Let me kind of explain. If I had 3/4, the number 3/4, if I wanted to, I could write that as 1/4 times 3, right? Would you agree with me? Yes. So that's what I'm going to do here. I'm going to rewrite this as 1 over my denominator times my numerator. So that we can see a little bit more clearly what all needs replacing and where it needs replacing. So I can replace this part right here with 1 over u squared. So again, we don't want to say 1 over u squared times x to the 4th minus 2. We don't want to mix our x's and our u's. What we want to do is we need something that will replace x to the 4th minus 2 dx. So what I'm going to do is come back to my u and take the derivative of both sides. Derivative of u is 1 du. And here we'll have 5x to the 4th minus 10 dx. So I still do not have anything that equals x to the 4th minus 2. What I have equals 5x to the 4th minus 10. What can we do to both sides to make it what I want? Divide by 5. That's right. So dividing by 5, same thing as multiplying by 1/5. And now I have something that equals x to the 4th minus 2 dx. Exactly. And so I will replace x to the 4th minus 2 dx with what it equals, 1/5 du. As soon as I've replaced all of my x's with u's, I pull out any numbers I might have. I'm going to rewrite this term. Is this a natural log right here? Nope. Because to be a natural log, it'd have to be 1 over u to the 1. So I'm going to pull it up to the top. And I'll have 1/5 u to the negative 2 plus 1 would be negative 1 divided by 1 plus c. And so I've got 1/5, but that u to the negative 1, I need to take that to the bottom, u to the positive 1 plus c. And then I need to replace the u. Oh, divided by negative 1, excuse me. So I have negative 1 over 5, and I'm going to replace my u plus c. I know what you're thinking. This is so much fun. All right. Moving on. Pause at any time in case you need to catch up. Or if you just enjoyed it so much you want to watch it again. Alright. It's part A here. So the square root is the same thing as to the 1/2 power. So that's still a bunch of stuff to a power. So I'm going to let u equal x cubed plus 3. I'm going to go ahead and separate my numerator from denominator. So this is the integral of 1 over, instead of the square root, I'm going to put x cubed plus 3 to the 1/2 times, so I'm separating my numerator and denominator, times 2x squared. You could put over 1 if you wanted to, but you don't have to. Dx. So I just separated my numerator and denominator so that I can see more clearly how to substitute everything. So now I can see I can replace this whole term right here. That's going to be the integral of 1 over u to the 1/2. I still need to replace 2x squared dx. So I'm going to come back to my u, and I'm going to take the derivative of both sides. 1 du equals 3x squared plus 0 dx. So I have 3x squared, and I need 2x squared. A couple of different things you could do here. My favorite thing to do is, anytime you have a number just multiplied in there, you could actually take that number and pull it outside, because it's just being multiplied. And so, instead of replacing 2x squared, now I just need to replace x squared dx. How can I make this x squared dx? Divide both sides by 3, or multiply both sides by 1/3. So since it wasn't an easy fix, and the 2 is being multiplied in there, I could just bring the 2 on the outside, and we'll worry about it after we integrate. And so I'm going to replace my x squared dx with 1/3 du. So I've replaced all of my x's with u terms. I'm now going to pull out my numbers. I already have a 2 out there. If I pull 1/3 out there, I would now have a 2/3. I'm going to bring this u to the top. This is not going to be a natural log answer because it's not u to the 1. It's u to the half. So I'll bring it to the top and make it -half. And now I'm going to integrate. So I have 2/3 u to the -half plus 1, which is +half, divided by +half, plus c. Dividing by half is the same thing as multiplying by 2/1. And so I end up with 4/3, and in place of u, I'm going to put what it equaled, plus c. All right. So back at the beginning, I'm going to scroll back a little bit, where I said I'm going to tell you how to choose your u. Of course, I'm scrolling and everything goes away. The only one we've talked about so far is if you have a bunch of stuff to a power. So we're going to talk about some more now. If you don't have a bunch of stuff to a power, but you have a numerator over a denominator, and there's no power involved, no exponent involved, the denominator is going to be your u. So if you have a numerator over a denominator, the denominator will be your u. And so I'm going back to example 2, part B here. We don't have stuff raised to a power, but we do have a denominator. So I'm going to let my u equal 7 minus 5x. So as of right now, I can replace that part with the integral of 1 over u. I still need to replace dx with something that equals it exactly. So I'm going to come to my u and take its derivative. Derivative of u is 1 du equals 0 minus 5 dx. So I have something that equals -5 dx. What I want it to equal is just dx. What do? I need to divide both sides by -5, or you can think of it as multiply both sides by -1/5. Now I have something that equals dx exactly. So I will replace it with -1/5 du. Once you have replaced all of your x values with u values, pull out any numbers you might have. Do we need to bring this to the top? If you did, and you went through the process, you will eventually see that red flag going off in your head, because anytime you have 1 over u to the 1, that's going to end up being a natural log. So this will be -1/5 natural log of the absolute value of u plus c. Replace your u. So -1/5 absolute value of 7 minus 5x plus c. All right, so another way to choose your u, I'm going to go back to the top. If you have a bunch of stuff to a power, that stuff is your u. If you just have a numerator over a denominator, denominator is your u. If you have e to anything, so if it's e to the x, the integral is e to the x. If it's, I'm not going to say anything, because we know the integral of e to the x is e to the x. And we also know the integral of e to just a number times x is just 1 over that number times e to the 5x. Let's see. So if you have e to a, I'm just going to say squiggle line here, power. And that power is not just x to the 1. If that power is the square root of x or x squared or anything other than x to the 1, then that exponent is your u. That exponent is your u. All right. Taking you back now to example 2, part C. So here we have a bunch of stuff going on, but we have an e. And this e has an exponent right there. So I'm going to let my u equal 2x cubed plus 4x. So right now, I'm able to replace that part with e to the u. Again, don't put e to the u times 3x squared plus 2 dx. You don't mix your x's and u's. What I need to do is I need something that will help me replace 3x squared plus 2 dx exactly. So I'm going to take the derivative of my u, and I get 1 du equals 6x squared plus 4 dx. What I need it to be is 3x squared plus 2 dx. What can I do to both sides to make that happen? Divide by 2, which is the same thing as multiplying by 1/2. So 3x squared plus 2. So now I have an exact match, so I will replace it with 1/2 du. Now e's are the best, because what's the integral of e to the u? E to the u. So I can pull my 1/2 out, and then I'm going to integrate. Integral of e to the u is e to the u plus c. And then just replace your u with what it equals. All right, let's do this next one. It has an e to an exponent that's not just x to the 1. So I'm going to let my u equal the exponent of e. And I can now replace this part right there with the integral of e to the u. I still need to replace 3x to the 5th dx. If I wanted to, I could go ahead and pull the 3 out right now. I'll wait and see if I need to, if it makes it complicated or not. So I'm going to take the derivative of u, and I get 1 du equals 6x to the 5th dx. So can we easily turn 6x to the 5th dx into 3x to the 5th dx? Yes, just divide both sides by 2. If that wasn't easy, then I would pull the 3 out, and all I would have to replace is x to the 5th dx. But it's easy, so we're going to divide both sides by 2 or multiply both sides by 1/2. And now we have an exact match. So I will replace it with 1/2 du. As soon as you replace all of your x terms with u terms, pull your numbers out. And then the integral of e to the u is e to the u. And then replace your u with what it equals. All right, one last helpful hint on how to choose your u value. So I'm going to go back up to the choosing your u. Of course, it always disappears when I scroll. There we go. All right, so if you have a bunch of stuff to a power, that's your u. If you just have numerator over denominator, denominator's your u. If you have e raised to something other than x to the 1, that's your u. And finally, if you have a natural log of something in your problem, that whole thing is your u. The entire log or natural log is your u. All right. So on example 3, we have a natural log in this problem. So I'm going to let my u, not be that marker, my u equal the natural log of x. Since this is a fraction, numerator over denominator, I am going to separate it. This is the same thing as, I can pull the 12 out front because it's just a number. And then I just have 1 over x times the natural log of x dx. So I pulled out my number, and then I separated my numerator and denominator. I can now replace that part right there with a u. So I'm going to have 12 integral of u. I still need to replace Oops, didn't mean to do that. I still need to replace 1 over x dx. So I'm going to come take the derivative of my u, and I get 1 du equals, derivative of natural log of x is 1 over x dx. I need to replace 1 over x dx, so it's an exact match without having to do anything. So I'll replace it with du. So integrating, I'll have 12u to the 2 divided by 2 plus c. So I have 6u squared plus c, and all I have left to do is put the u back in. Notice I don't have any absolute value signs anywhere, and that's because I'm not the one who put the natural log in the problem. It was already in the problem. All right. 2 more like that, and then we kind of take a shift. So here we're going to have our u equals 2x squared plus 6x minus 10. I'm going to separate numerator denominator. So 1 over 2x squared plus 6x minus 10 times 2x plus 3 dx. So I just shifted and separated my numerator and my denominator. Then I could see that I can replace this part right there. That's going to be the integral of 1 over u to the 4th. I still need to replace 2x plus 3 dx. So if I take the derivative of both sides, I get 1 du equals 4x plus 6 dx. What I need is 2x plus 3 dx. How can I make that happen? Yep, I can divide both sides by 2 or multiply both sides by half. So I'm going to have 1/2 du equals 2x plus 3 dx. So I will replace it with 1/2 du. And that'll equal 1/2. I'm going to bring that u up to the top and make it to the negative 4. Now I'm going to integrate. So I have 1/2 u to the negative 4 plus 1, which is negative 3, divided by negative 3 plus c. So dividing by negative 3 over 1 is the same thing as multiplying by negative 1 over 3. So I have negative 1/6, and then that u to the negative 3 needs to come to the denominator to become positive 3. All I have left to do is I need to replace the u with what it equals. And there we go. All right, one more problem. So it's a fraction. I can separate this. I can make it 1 over, the 5th root is the same as the 1/5 power of all that, times my numerator. So to have a bunch of stuff raised to a power, that's what I'm going to let my u equal. So my u will equal 2x squared plus 5. And then I can go ahead and replace this part right here with the integral of 1 over u to the 1/5. I still need to replace x dx. So if I take the derivative of my u, I get 1 du equals 4x to the 1 dx. So what I have equals 4x dx. I want it to equal x dx. So I divide both sides by 4. And now I have an exact match. So 1/4 du equals x dx. I will replace it down here. As soon as you get all of your x terms replaced with all of your u terms, you can then pull out any numbers you might have. I'm going to pull my u up to the top and make it -1/5. Then I can integrate. So I have 1/4 u, -1/5 plus 1. If you need to use your calculator, do so. But -1/5 plus 1 becomes 4/5. Divide by my new exponent, plus c. Dividing by 4/5 is the same thing as multiplying by 5/4. And so I have 5/16, and I'm going to replace my u to the 4/5 plus c. Yay! All right, so we have 2 more pages, but you've gotten through the hardest of the U-substitution. The next page is still U-substitution, but it has a little bit of a different twist. Not hard, just different. So you don't know it by looking at it, but you'll see what I mean here in just a second. So let me just point out, we're not able to multiply the x into the x plus 6 to the 8th because it's to the 8th. If we wanted to multiply the x in there, we would have to FOIL this term out 8 times, which nobody's going to do, even if you're staying at home all the time. All right, so what I'm going to do is I'm going to do my typical U-substitution, or start off that way at least, and I'm going to let my u equal the stuff being raised to the power. So I can replace that part right there with u to the 8. Now I still need to replace the x and the dx. You might notice I highlighted them different colors this time because I already know what's going to happen. So coming up, taking the derivative of my u, I get 1 du equals 1 dx. Now what I need is x dx. Here's the rule. You can only multiply or divide each side by a number, not by x, not by a variable. You can't do that. So this part will replace the dx for me. So I'll go ahead and put that in there. But I still need to replace the x. So what I'm going to do is I'm going to solve the u that I just found for x. I subtract 6 to the other side. And now I have a value for x. X equals u minus 6. And I was able to replace all 3 parts. So now look at this. We can multiply u to the 8th into this one because it's to the 1 power. So multiplying them in, when you multiply like bases, you add the exponents. So u to the 8th times u to the 1 is u to the 9th minus 6u to the 8th. Then I'm going to integrate. So I have u to the 10 divided by 10 minus 6u to the 9 divided by 9 plus c. So I end up with 1/10, and instead of u, I'm going to put x plus 6 back in, minus 6/9, I can take a 3 out of both, so that'll be 2/3, and instead of u, I'm going to put what it equals back in. All right, we're going to practice 2 more of those just to make sure you understand them. Again, and just by looking at it, you don't know that's going to happen. So let's just start off as if we don't know that's going to happen. So cube root, same thing as 1/3 power. So I'm going to let my u equal x minus 2 because that's being raised to a power. So I'm going to go ahead and replace this part right there with with cube root of u, or u to the 1/3 power. I still need to replace x dx. So I'm going to take the derivative of my u, and I get 1 du equals 1 dx. And here's where I realize my issue. I can't multiply both sides by x, even though I need to replace x dx. Right now I can only replace the dx part. So I can replace it with du. I have to figure out what else to do to replace x. So I'm going to solve my u equation for x. I'll add 2 to the other side. And then this is what I'm going to put in for x. So I've replaced all of my x's with u's. I can multiply this through because it's to the 1 power. Again, multiplying like bases, you add exponents. So u to the 1/3 times u to the 1. 1/3 plus 1 is 4/3. Plus 2u to the 1/3 du. Integrating, I'm going to get u to the 4/3 plus 1, which is 7/3 divided by 7/3, plus 2u to the 1/3 plus 1, which is 4/3 divided by 4/3, plus c. Dividing by a fraction, same thing as multiplying by the reciprocal. So I have 3/7 u to the 7/3 plus 3/4 times 2 u to the 4/3 plus c. So I end up with 3/7. I'm going to replace my u to the 7/3 plus, we multiply these, we get 6/4, which I can take a 2 out of both, so 3/2. Replace my u plus c. All right, one more of these. It's a fraction, so I'm going to think of it as 1 over, instead of square root, I'm going to write x plus 5 to the half times x dx. I'm going to choose my u. My u is x plus 5. Derivative of u would be 1 du equals 1 dx. Okay, so I need to replace x dx. So this part right here is the integral of 1 over u to the half. I still need to replace x dx, but what I have will only replace the dx. So I'm going to replace the dx with du. So I still need to replace the x. I'm going to solve my u value for x. And I get u minus 5 equals x. So I'll replace my x with u minus 5. All right, so I'm going to bring this up to the top. So I have u to the negative half times u minus 5. I can multiply that through because it's just to the 1 power. And remember, when you're multiplying like bases, you add the exponents. So negative half plus 1 is 1/2 minus 5u to the negative half du. And now I can integrate. So integrating, I would get u to the 3/2 divided by 3/2 minus 5u. Negative half plus 1 is positive half divided by positive half plus c. Dividing by a fraction, same thing as multiplying by the reciprocal. So I'll have 2/3, and I'm going to replace my u with what it equals. Dividing by half, same thing as multiplying by 2. So 2 times 5 is 10. Replace my u. All right. So we've seen it all for the U-substitution. I just want to do 2 word problems with you that show you that you don't always have a plus c at the end. All right. So the rate of healing for a skin wound in square centimeters per day, yeah, that's kind of gross, is approximated by that derivative right there. If the initial wound has an area of 12 square centimeters, what will its area, A of t, be after t days? So it's saying initially, at time 0, the area was 12 square centimeters. So it gave us a point, basically. So we first want to find the original function, the area function. We can find the original function by taking the antiderivative of the derivative. So I'm going to be integrating negative 0.9 e to the negative 0.1 t with respect to time. Now this actually is not even a U-substitution problem. This is from 15.1. So remember what you do when you have a number and it's just t to the 1. You want to do 1 over that. So I'm going to have, I still have this number there, but then I'm going to have 1 over the number, and then just copy the e again, plus c. Okay, going to come up here and remind you, if we had e to the 5t, the integral is 1 over that number, e to the 5t. That's what I just did. This part right here I'm going to put in my calculator, see what that gives me. And so I have negative 0.9 times 1 divided by negative 0.1. And I get 9. So that equals 9e to the negative 0.1t plus c. So this is A of t so far. We need to find what c is. So they gave us a point. When time is 0, the area is 12. I'm going to plug that in. 12 equals 9e to the negative 0.1 times 0 plus c. So 12 equals 9e, anything times 0 is 0 plus c. E to the 0, if you don't know what that is, type it in your calculator, but e to the 0 equals 1. So this is 12 equals 9 times 1 plus c. Subtract my 9 from both sides and we get 3 equals c. And so the area, A of t, is 9e to the negative 0.1 t plus 3. That is the area function. And then it says, what about after, so that's after t days, just in general, after t days. And then it says, what about after 5 days? So we'd want to put a 5 in there. So we'd have 9e to the negative 0.1 times 5 plus 3. And we can type that in our calculator. 9e to the negative 0.1 times 5 plus 3. And we get 8.46. So 8.46 square centimeters. All right, one more. Just looking at these functions real quick. Look, that one was just e to a number t to the 1. Okay, so we just had to do the 1 over the number. Whereas this one down here is e to negative 4x squared. So this is going to have to do a little U-substitution because it's not just x to the 1. So it says find the cost function for a koozie manufacturer if the marginal cost, which is the derivative of the cost, is given here, where x is the number of cases of koozies produced. Assume fixed costs. That means when x equals 0, the costs are $125. All right, so to find the cost function, I'm going to take the antiderivative of the derivative. So I'm taking the antiderivative of 24x e to the negative 4x squared dx. So I have a number in front. I could always pull it out if it doesn't get easily replaced. So keep that in mind. Choosing my u, since there's an e in the problem, I'm going to let u equal negative 4x squared. So I can replace that part with e to the u. I still need to replace 24x dx, and if I can't replace the 24 easily, I'll just pull it out front. So taking the derivative of both sides, derivative of u is 1 du equals negative 8x dx. So I have negative 8x dx. What I want is 24x dx. Can we make negative 8 into 24? Yes, if we multiply both sides by a negative 3, that would become 24x dx, which is exactly what we want. So I have an exact replacement. I will replace it with negative 3 du. As soon as I've replaced all of my x terms with u terms, I'm going to pull out the negative 3. And then the integral of e to the u is e to the u. So right now I have my cost function equals negative 3e. I'm going to put my u back in, negative 4x squared plus my constant. Now don't get confused. This c is cost, this c is constant. Sometimes when I have a c in the problem, I'll put a k for constant, just so I'm not confused. And we have a point right here. When x equals 0, the cost is 125. So I'm going to put that in and solve for my constant. And that would be 0 squared. So I get 125 equals negative 3 e to the 0. Remember, e to the 0 just equals 1. So this is negative 3 times 1. And if I add 3 to both sides, I get 128 equals my constant. And so my cost function is going to be negative 3 e to the negative 4x squared plus 128.